Experiment number 2, identifying a material from its resistivity. Objectives: to determine the resistivity of a metal wire. Safety: do not measure current for zero length. This will send a damaging current through the ammeter. Apparatus: power supply, nichrome wire. I fixed it between two holes. So this is the nichrome wire. Variable resistor, digital ammeter, digital voltmeter, connecting wires, micrometer screw gauge. Procedures: we use the micrometer screw gauge to measure the diameter of the nichrome wire at 3 different places. Now, first of all, we have to check the zero of the nichrome. It is perfect. And then we put the micrometer in this position and gently we move the screw out. Then we find the measure. It is 0.5 plus 21. Then the first measurement of diameter, it is 0.5 plus 0.21. It is 0.71 millimeter. We have to convert to meter at the end. At another position, because there are three different positions, we fix. Yes. Now it is 0.5 plus 0. The rotational is 19, so it is 0.5 plus 0.19. Answer is 0.69 millimeter. At the third position of the wire, it is 0.5 plus 21 rotational. So 0.5 plus 0.21, it is 0.71 millimeter. We take the average. The average is 0.7 millimeter. We have to convert millimeter to meter, multiply 10 power negative 3. So the diameter equals 7.03 times 10 power negative 4 meter. Then the cross-section area of the wire is 3.89 multiply 10 power negative 7 meter squared. The results: the average diameter is 7.03 times 10 power negative 4 meter. The cross-section area is pi d squared. The diameter denoted by d, the cross-section area is pi d squared divided by 4. Our value is 3.89 times 10 power negative 4 meter squared. Set up the circuit as shown in the figure opposite. So, starting. From the power supply to the ammeter, and from the ammeter we use the crocodile wire. From the ammeter to here we divide the wire into parts. Each part is 10 centimeter. So this is 10, this is 10, 20, 30, 40, 50. Okay, now we fix the crocodile at the start of the wire. Here we have, it's better to measure from this position. Then we take here, then we measure 10 centimeter from this position. It's better. Then we take 10 centimeter from our position of crocodile wire. Then it's here. This is 10 centimeter. So I use another crocodile wire after 10 centimeter exactly. I fix it here in the rheostat, and from rheostat to the power supply. I check my connection. We check the connection. Now it's perfect. But we have to check the distance exactly. It must be 10 centimeter. Yes. So this point will be fixed, but this point will be moved until to be 10, 20, 30, and so on. Next step, we connect the voltmeter in parallel. We use the crocodile clips, crocodile wire. Yeah. Take care exactly on the top to be exactly at 10 centimeter. Now I check. Because the voltage is negative, just to exchange the wire. Check again. It's okay. Now, we check the distance again to be more perfect. Yes, it's 10 centimeter. So the length is 10 centimeter. After each reading, immediately we switch off the power supply. Now, the first reading of the length is 10 centimeter, 20, 30, 40, 50, and now the voltage in case of 10 centimeter. The voltage is 0.07. The corresponding current is 0.14. We add another 10 centimeter here. Then it will be here. Exactly. Just I move this cursor. I move this crocodile, but it must be stable. Okay. I check the distance again. Must be 20 centimeter. Exactly, it's a 20 centimeter. Now I take the second reading when the length is 20 centimeter. The voltage is 0.12. The corresponding current is 0.14. We increase the distance. We add more 10 centimeter. Now, okay. Now the distance is exactly 30 centimeter, the third trial. The voltage is 0.16. Of course, the current will be the same because it is series connection. So no change in the current, but just we check. One more reading. We add 10 centimeter to the wire. We take the reading of voltmeter, 0.21. Of course, the current is the same, 0.14. The last reading, we add 10 centimeter more. here. Now the length of the wire is 50 centimeter. We take the reading of voltmeter. It is 0.29. Of course, the ammeter reading is 0.14. The same. We calculate the resistance in each case. The resistance is V over I. The resistance increases as the length increases. It's a direct proportion. Equals V over I. So in each case, we calculate the value of resistance. You note that the resistance increases as the length increases because R proportional directly to the length. Calculations and analysis. Plot a graph of resistance R of the wire against its length. On y-axis, this is R. It's in ohms. Because the values are little less, we can multiply by 10. Then we multiply this value by 10 to the power -1, and our results, we multiply it by 10. 2, 4. This value has mistake, so it's 2.07. But here the maximum value is 20. Then we have to continue 16, 18, 20, 22. Remember, we multiply the value by 10 power -1. On x-axis, we represent the length in meter, but because our length it was in centimeter, we multiply by 10 to the power -2. 10, 20, and so on. Of course, because R proportional directly to the length, then the first point that we have to represent is 0 and 0. So this point included. When the length is 0, the resistance is 0. And then the second point, when the length is 10, here we multiply by 10 to the power 1, so it's 5. So when the length is 10, when the length is 10 centimeter, the resistance is 5. So at the middle, here, this is a mistake, 0.16 divided by 0.14. This is also here. It's 1.14. The third value here, when the length is 30 centimeter, the resistance is 11.4, and we multiply by 10 to the power -1, so it's 11.4. It's here 11 at the middle, then 11.4, it's here. Now we draw the best fit line. It is a line in between the points. This is the best fit line. We find the gradient. Now we find the gradient equals y2 minus y1 over x2 minus x1. This is y2. It is 14.6 minus y1 is 0 over x2. This is 35 okay, minus 0. But here, remember to multiply y by 10 power negative 1 and x multiply 10 power negative 2. We find the value. The answer is 4.17. What does the value of gradient represent? We know that R equals rho L over A, or we can write it as rho A over L. Then R equals the gradient multiply L. So the gradient represents rho divided by the area. Next question, calculate the resistivity rho. Then we write here rho over A equal the gradient equals 4.17. So the resistivity equal the area, the cross-section area, multiply 4.17. The cross-section area, we found it before, it is 3.89 multiply 10 power negative 7. So 3.89 multiply 10 power negative 7 multiply 4.17. 1.62 multiply by 10 to the power negative 6 ohm meter. Use the internet to compare your calculated value of rho. This is the calculated value of rho to the actual value. The range of value, the range of values of resistivity of nichrome wire from the internet 1.10 multiply 10 to the power negative 6 ohm meter to 1.50 multiply 10 to the power negative 6 ohm meter. Our value is little out the range. Our calculated value is 0.12 away from the range of values. What are the sources of error in this experiment? The measurement of the wire was not accurate. The measurement of the wire L was not accurate. Number two, because the resistivity depends on the gradient of the best fit line, so this is one of the source of the error. What about the conclusion? We did this experiment to calculate the resistivity of the nichrome wire. Our value is 1 point, our value is 1.62 times the 10 power negative 6 ohm meter, which is little outside the range of the values, because the range is from 1.1 to 1.5 times 10 power negative 6. Why it is not in the range? Because two reasons. The first reason is the measurement of the length of the wire in each trial. The second reason, the best fit line, because the gradient depends on our choice of the best fit line. But our value is acceptable. Thank you.